We've been talking about the definite integral for quite a few lessons now, so let me formally give you the definition of the definite integral. In our previous examples of Riemann sums, we've worked with a finite number of rectangles. When we put this together with our limit work, remember we talked about having 5 rectangles and then 50 rectangles, and we could take n, which was the number of rectangles, to infinity. And so then we would have sums with an infinite number of rectangles, and this gives us, this is powerful, this will give us the exact area trapped in the plane between a function, the horizontal axis, over some interval. So when we put the limit notation in front of our sum, right, I don't know if you know what all this notation means, but this means the sum. That capital sigma there means sum, where we start with the first rectangle and we stop at n number of rectangles, and we are taking n to infinity. So we have infinitely many rectangles, and we are taking the sums because the definition, the sum we have here, are the products of our heights and our widths. So this is the definition of what the definite integral is. We've been working with the indefinite integral, which said to find the antiderivative function with respect to x. When we put numbers in front of that integral notation, we're now talking about the definite integral. So now we can find the sum of the exact area using infinitely many rectangles. Also, we find that our Riemann sums that we've been doing wind up being approximations for definite integrals that will approximately get us the area trapped in the plane from a up to b, x equal a to x equal b, under the function f of x, in between, I say under, I shouldn't say, I should say trapped between the function f of x and its horizontal axis, because it's not just under, it could be above, but it's trapped between the function and its horizontal axis. So there's the definition of the definite integral. We know that we have limits of integration. The lower limit of integration is a, the upper limit of integration is b. That's what this notation means. And this gives us the signed area. Area below the x-axis will be negative area, just like Riemann said. Area above the x-axis will be positive area. So we get that from the work that Riemann did in the plane when he was accumulating area in the plane. So this gives us the signed area of the region trapped between the curve, which is the function y equals f of x, and the horizontal axis over the interval from a up to b. It is true that our lower limit of integration always needs to be, we'll put lower limit, our lower limit of integration should always be less than our upper limit of integration. And what this means in practicality is that we always accumulate area from left to right. We always integrate or accumulate area trapped in the plane because we assume a is less than b. We always integrate or accumulate area from left to right. All right? If, for whatever reason, our limits are given to us in the opposite order. Let's say they ask us to integrate from -3 to -10. Well, moving along the x-axis from left to right, we're going to hit -10 before we're going to hit -3. So this is not the case where the lower limit is less than the upper limit. If we ever encounter that, we can fix that by accumulating in the opposite direction, which is what that negative out in front of the definite integral means. So we would equivalently accumulate this as the opposite of the accumulation from -10 up to -3. All right, so that's really a property of the definite integral that I go ahead and introduce now because it's really straightforward, but it's a property of the definite integral that we can use if we need to. And it turns out that the accumulated area in the plane does give us the signed area. We are going to accumulate and add up all the positive area, and we're going to subtract all of the negative area. So anything that is above the x-axis will be positive, anything that's below the x-axis will be negative. We also must note that x is a general variable. I've said over and over and over that we're not going to let notation trip us up. Just because I teach using y and x doesn't mean you won't encounter other variables. All of the relationships that we're going to be taught that hold true and all the properties of the definite integral work for any variable. Remember, this is still the with respect to. So if we have a function in t, it's asking us to find the antiderivative with respect to t. Here it's asking us to integrate or find the signed area, to accumulate the area trapped in the plane between this curve and its horizontal t-axis. Here we have a horizontal s-axis. So not every function is integrable everywhere. We must have a bound. We need to have an upper bound for anything that is above the horizontal axis. Here is an upper bound to any area that we want to accumulate from, let's say, any values greater than 0 up to positive infinity. We have an upper bound, that is bounded area. And any lower bound for any area that might be below the x-axis. So here is bounded area from negative infinity up to but not including 0, because clearly we're not bounded there. So any function that is integrable on a closed interval must be bounded on that interval. Let's say that I wanted you to accumulate area in the plane from 1 up to, I don't know, 1,000. Underneath this function, hopefully you recognize this is the parent function, y equals 1 over x. So I want you to accumulate the area trapped in the plane, starting at x equal 1, stopping at x equal 1,000, trapped in between this function and the horizontal axis with respect to x. Well, that's a perfectly bounded area. This is the area that it's talking about. And we would continue to add that area up until x equaled 1,000. So as long as we are bounded on the closed interval, then we can integrate, or we can accumulate that area. If we throw out the interval over which the function is not bounded, then we could find the area for the remainder of the curve. In other words, if I ask you to find the accumulated area over the interval from -1 to 1, for the function f of x equals 1 over x, you have issues. That function's not bounded at x equals 0. You can't accumulate the area there. All right? So make sure that you're bounded on the interval from your lower limit of integration to your upper limit of integration. So how do we calculate definite integrals? How do we accumulate this area in the plane? Well, a lot of that is going to depend on context. We'll take it on a case-by-case basis. Let's talk about, and here formally is that integrability theorem that I was talking about on the last slide. If f is bounded on the closed interval a up to b, and if it is continuous there, except at a finite number of points, then f is integrable on that closed interval. And particularly if f is continuous on the whole interval, then it's integrable on the whole interval. All right, so again, the definite integral. Our work will look exactly like it did on the last lesson. The only change is the above notation. Instead of being told to use a Riemann sum and instead of being told to approximate the area, we're going to use this to tell you to find the area, right, in the plane, between f of x and the horizontal or x-axis, starting at A and stopping at B. We'll learn how to find the exact area using the definite integral. It's a really important fundamental theorem. It's in the next lesson coming up. But for now, I want you to understand that this notation can be approximated by the Riemann sums using the finite number of rectangles that we've been doing up to this point. So our work is going to look the same as we have done before, and we'll be given specific instructions on how we're going to approximate that area. But now we know that we can approximate this using the Riemann sums, left endpoint, right endpoint, midpoint, whatever we're going to be told. But that's what this notation is telling us to do. Instead of saying that the integral from 0 to 2 of our function equals this accumulated area, we will say it is approximated by. Okay, we're going to use approximated by on this function. Again, we're going to be instructed in every problem which Riemann sum to use. They'll tell you, use a left endpoint Riemann sum, or using a right endpoint Riemann sum, or a midpoint Riemann sum, just like this. Let's use a midpoint Riemann sum. We start by drawing the bottom of all the rectangles, right? We're going to draw the bottom of all the rectangles over our interval. So we are going from 0 to 2 along the horizontal axis. And how many rectangles should we use? We can use 1, we can use 2. Let's use 4. Let's use 4 rectangles. And again, we'll be told how many rectangles to use. And we know that the more rectangles we use, the more accurate the approximation of the area would be. So let's label all the x-axis tick marks from 0 to 2. We really don't care exactly what the area looks like in the plane because our Riemann sums are going to take care of that for us. So our area, all of our widths on all 4 rectangles are standard, just like the work we've been doing before. So there's our widths. Now we need the sum of our heights, and we're supposed to use midpoints. So we need this value, this value, this value, and this value, and we're going to plug it into our function y equals x plus 1. So remember all that. So this is 1/4. Here is 3/4. 4/4, this is 5/4, and this is 7/4. So our first height, coming from this midpoint, I put that value into my function, which takes everything that I feed it and adds 1, and there's my first height. My second height comes from the second midpoint. My third height comes from the third midpoint, and my fourth height comes from the fourth midpoint. So there is the approximation of the area in the plane, starting at 0, stopping at 2, trapped in between this function and the horizontal axis. All right, so again, just like our work that we had been doing before. Here are some properties of the definite integral, just like we had properties of derivatives. We know derivatives break up over addition and they break up over subtraction, but they don't break up over multiplication and division. So those properties, or those rules that we know about derivatives, definite integrals have rules that they must follow as well, things that are always true. So if this is always true about a definite integral, it's a property that we can count on, and we can apply it in any situation that we might need when they ask us to use the definite integral. I'm close to the end of this video, so I'm going to start a new video and we'll go over these properties of the definite integral in the next video.